Speaker for today is Chris Peters, and he will tell us everything we always wanted to know about stage and vibration.
I hope so. So this talk today will be about the Hitchin moduli spaces and Hitchin fibration. But before that, I will recall a little bit. I think we saw it in one of the previous talks already. I want to set my notations and notions right. So this is what I call moduli space MG. So I work over C. So the setting is the following. I have C is just a complete projective curve. Complete smooth projective curve over C, and it will be of genus G. And I am mostly interested in this talk in vector bundles, which I will denote E with a little arrow, vector bundles over C. So vector bundle over the curve C, and G will be either GLN or SLN or PGLN. And so MG will be the moduli space of stable vector bundles, moduli space of stable vector bundles, stable, with a G structure. So with the G structure, GLN just means of rank n. This is the only is equivalent. SLN means that you fix a determinate line bond, and most of the time it must be 0. So trivial determinant. And PGLN, okay, that's yes, just modulo an action of C star.
So then there is no E actually.
Huh?
Then there is no E in the PGLN case.
There is no E, no. But I still want to speak about this moduli space. So, now there is one thing that in the first talk has been glossed over a bit, namely, you have to, if you want to speak about the GLN bundle, you have to fix a degree. So, in fact, if I speak of a GLN bundle, one has to fix some degree D. And so you actually should write it then as ND. Right. ND. Otherwise, it's not even a variety. So you have to fix the degree.
So is this the degree of the determinant?
Where D is the degree of the determinant of E. Yes.
When you say it's not, is that because otherwise it would be an infinite disjoint union of?
Yeah. Now, so for a while I will work with this space, and the theorem that I recall, I assume. Well, okay. Let's fix. So we take this case where we fix the D, and we assume that this D is co-prime with M. And in that case, it's known that N, I will now lose the decoration, which is NdG, is smooth projective variety, and its dimension is N square G minus 1 plus 1. So we'll write dn for this dimension. This is the first assertion. The second assertion, well, let me write it a little bit differently. For every class, isomorphism class E in this space, we can look at the cotangent space, and I claim that this is canonically isomorphic with the endomorphism, the twisted endomorphisms, namely you have to twist by omega, and I'm lazy, I don't want to write down all the time canonical bundle of C, so omega is the canonical bundle of C. Now, there is, maybe I should also write a variant here. And this is the variant because this plays a big role. The G is SLN. What is the variant here? Well, I will call the corresponding moduli space N with a little 0. So it's not to be confused with N of degree 0. But in fact, you can, in this case, also compute the dimension of the moduli space. It's a little bit different, N minus 1 squared times G. And you can also identify the tangent space. In this case, this will be canonically isomorphic to the traceless. So into 0 again, this means traceless endomorphism. So endomorphisms of trace 0.
So you have G not 0 then here, right?
Huh?
Because G should not be 0, I think. You get negative numbers.
Yes, it's, I think we only do it for genus at least 2.
I don't
I'm
know.
not sure.
2. Okay.
Yeah. Okay, so let's.
But it's still smooth and projective in the SLN case.
Yes. And in fact, I will give a little description of this. Namely, what is the link between the two? Maybe I'll do it here. I have a little bit of space. So what's the link between the two? Well, in general, if I have ND, GLN, I can make the determinant of E. And then I go to the Jacobian, but not the Jacobian, Jacobian of degree D line bundles. C. And what is N0? In fact, that is the inverse image of 0 in case D equals 0. Otherwise, the other, if you take a line bundle and the inverse image, then you get these twisted these twisted bundles. So those form not the bundle N0, but N with an L here. So this is otherwise, and L is the determinant, where L in this case may have any degree, but N0 you have to have degree 0.
So sorry, the assumption that D is co-prime to 1.
It's
So to
only
get-
needed for smoothness.
Right, so for SLN you need to take a twisted one to get it. You need to choose a twisted one to get smoothness for the SLN one, then.
Or take n equals 1, but that's less interesting.
If you take D, well, I'm not so sure whether, because I do not claim the smoothness for, well, okay, yes, it could be that the fibers hit singularities. Yeah, that's true. But I don't worry too much about singularities here, because everything can be resolved. Know exactly what the singularities are. Okay, so let me just give a stupid proof, assuming a smoothness of these two facts. Namely, we just have to calculate, well, first of all, what is the tangent space if it smooth is just, so proof assuming smoothness, and it's just the Zariski tangent space, and this is the H1 of C and E. Now you dualize, and you get this. So this is using steric duality. This is the explanation. And now, what about the dimension of n? So this is, and the same for traceless and other prisms. And then what about the dimensions? Well, this is just Riemann-Roch, of course. So you have to calculate these dimensions, H0 of, let's say, just the easiest. Well, the easiest is this. And now you have to use that a stable vector bundle only has, the only global endomorphisms are the homotopes. So this is one dimensional. And now Riemann-Roch gives the difference. Namely, you calculate it's minus n squared g minus 1. So the H1, which is the dimensions of the tangent space, so the dimension of the space n itself, the H1 and the E is just what it should be. So n squared g minus 1 plus.
How did the n get in there? Because you said end of E is just O.
Huh?
Oh, the H0? No.
The H, there's the H1.
So the
Here the n is
okay,
Riemann-Roch.
the E is a bigger sheaf.
Yeah. E,
Yeah.
it's
Of rank n squared.
n squared is the,
Yeah.
the,
Okay,
the
that's
rank.
n squared for the rank. Yeah.
Yeah, it's the
Okay.
rank of this.
Yeah, yeah.
And if you do the same trick with n0, then this becomes 0, and the rank of this one is n squared minus 1, so this explains the difference.
Okay.
Okay. So now you see an important point already coming up, namely every element in the cotangent space is an endomorphism of this bundle, and this is precisely a Higgs field. So this corresponds to Higgs field. And in fact, that's also the motivation of Hitchin. Let me try to explain this. This is the second part. Namely, what is the, can I describe so-called Hitchin fibration on the cotangent bundle? Where does it come from? Well, these Higgs fields, I will call them, I will use the letter phi for them. So I pick now, so I want to describe elements of this guy. So those are exactly Higgs bundles, so E plus the phi. And if I take a point on the base, the curve C, then I have an endomorphism of the vector space. So this is an endomorphism, global endomorphism of the fiber tensor omega x, and associated to an endomorphism of a vector space, which is a twisted endomorphism. So what matters is this guy here. I can introduce the characteristic polynomial. So, characteristic polynomial of this guy. Phi x. This is just the determinant of x times the identity minus phi x. And this looks as follows. I don't care. I just want to fix notation here. So I get coefficients which end with a and x. And these coefficients, well, they belong to this is in omega, the fiber omega x, and this belongs canonically to omega x tensor n. So if I let x move, so if I have a global section here of this guy, so E phi gives now, so this gives globally a P phi, and this is a polynomial, but if you look at the coefficients of this polynomial, I will write it as an element in the direct sum of H0 in the various powers of omega. Tensor J, where J runs from 1 to n. So this is those are the coefficients of the polynomial. So I identify the polynomial with its coefficients, which I made. Okay? Now, and that's the Hitchin fibration. The Hitchin fibration associates to a point here in the cotangent bundle this element. And so if I use the letter A as in the article for this direct sum, and A0 for the direct sum, where I start with 2. Yeah, you see, if I have a traceless one, where is the trace? This guy is sitting here. So traceless things miss the first summand. So in the case of GLL, you get the Hitchin fibration, which goes from the cotangent space to the stable vector, moduli space of stable vector bundles to A. This is the Hitchin map. And in the case of SLN, it goes from the cotangent space to the traceless endomorphisms of A0. So that's the Hitchin map. Now, what is remarkable here is if you start counting dimensions. Because, okay, this is a construction, what can you do with it? But now it turns out that this space, just an affine space, has the same dimension as the dimension of the moduli space. This is double the dimension. And you expect, I will explain this, you expect that the fibers have also the same dimension. So let me formulate a proposition here. Of course, I'm not giving a good proof, proposition before the proof. What is the proposition? Well, as I said, the dimension A is Dn, and with the little zeros in the case of A0, and the dimension of the fiber, the inverse of A, is also here, is, well, it's not really a proof, but at least an indication of proof. First of all, this is easy. You just calculate with Riemann-Roch what this is. This is G. This H1. You can also, A0 omega 2. You can also calculate with Riemann-Roch is 3 times G minus 1, but I write this as G minus 1 plus 1. Go on until omega n. Here I find 2n minus 1 times G minus 1. And then you ask your first year students what is the answer when you sum up everything. Then you get n squared times G minus 1. This is the reason why I left out the 1. And you find this. Hey, this is the miracle. Now, 2 is just simply what I said. You expect that this map P is submersive, and it is an algebraic map. An algebraic. And now you count the dimensions. Dimension of the fiber is the dimension of its cotangent space, with which is 2 minus the dimension of A. And this is again here. Okay, so now you have done some numerology, and you feel maybe motivated to do some real work? Well, first maybe I should say something about the background, because this in itself is good for general education on the one hand. On the other hand, it motivates to guess something, which is important in mathematics, to make the right guesses. Okay, so so I make a remark which has nothing to do with just motivation, but it helps a little bit, certainly for people that come from that direction. Namely, as any cotangent bundle, this is a symplectic, it is a complex manifold, so it is a complex symplectic manifold. I'm not going to define what it is, it just, and what does P do? P how should I yeah, this gives, you can think of it as dn holomorphic functions. And if you have a symplectic variety, then you have a Poisson bracket, the Poisson commute. This is not hard to verify if you know your symplectic geometry. It's just a local calculation. But now the fibers are exactly where all of these functions have one constant value. So the fibers turn out to be tangent to dn Hamiltonian vector fields. Defined by those holomorphic functions. Okay. Every function defines such a vector field. And now you have an integrable Hamiltonian system. These define an integrable Hamiltonian system. And the leaves, so the leaves on which these functions are constant are of course the fibers of this animal, of this P, this Hitchin map. Fibers. This is general theory of integrable Hamiltonian systems. The fibers are open submanifolds of abelian varieties. So this follows from general theory. And the question is, of course, if you know that, if you know this general theory, where is the abelian variety? Can you explain the abelian variety? And this is the second stage in the picture. Namely, the question is, can you identify the fibers? What can you say about them? And once you do that, you can answer this question. So there is a system family of abelian varieties lurking in the background. Question, can you explain it geometrically? This is what Hitchin, I think, realized, coming from the integrable systems side. And once you pose the question, the answer is quite natural, but it's nice. So let me make a picture. Here I have the moduli space N, and here I have the cotangent bundle, the natural projection. On the other hand, I have my A and my projection P. So over a point A, which we call was an n-tuple of element of sections in various line bonds, twist powers of the canonical bundle, and I'm interested in finding this fiber. So this is P. What is it? So this is part 3 of the talk. What are the fibers? Now, I have this polynomial which is associated to phi. So I'm looking for phi such that the polynomial is exactly this. So now A is fixed, and I have this polynomial which is now x to the n plus a1 n minus 1 plus an. Now what can I do if I have a polynomial like this? Well, I can look at its roots, lambda 1 up to the lambda n. And those a's were sections, so in fact it's better to think of them as things that depend on x. So also these lambdas depend on x. Now you can guess what you can do, namely over every point. So here I have somehow C and I have point x. I have n roots. So over it I have n roots, lambda 1 back to lambda x. And I vary x, and I expect that this gives you a ramified cover defined by the roots. Of course, you must make this precise. How do you do this? And this is what I will tell you.
So where do these roots live? Or maybe that's part of what you're about to...
I'm going to.
Yeah, sorry.
So once you have this idea that, which is very familiar for people who do local analytic geometry, because you construct a cover from certain polynomials, for instance x squared equal to a, where a is a function, then the root is the Riemann surface, and this is exactly a Riemann surface construction, but then not with functions, but with sections in a line bundle. So it's very similar. And now you can ask yourself, except, well, phi is an operator, so except, you still have your vector bundle. So except for the eigenvalues, you also have the eigenspaces. And with every lambda x, I have an eigenspace sitting here. Eigenspace E1x EX. But this defines a line bundle, at least in good cases, ideally. So now, this object, where I have fixed A, but I still have my E, gives me a line bundle on CA. If I'm lucky, the genus of A is exactly right, so that the Picard group of this bundle has dimension dn. So the genus should be dn, if I'm lucky. Well, of course, everything works out that way, and your abelian variety is exactly Picard group, which you get in that way. That's what is behind. So let me write it down. So this was the rough idea. Now, what is the statement? Precise statement. I shall make a few calculations to convince you. So, yes, so you can make it precise. I think I have somewhere. I should have missed it. Yes, so the proposition following. It's true that the genus of all those curves are dn, and it's also true that well, so I will define this LA. There exists a line bundle on CA which, it's a line bundle provided CA is a smooth curve. And this is one of the technical difficulties, because if you are not lucky, then your curve will have singularities. So, but generically, it will be a smooth curve. So this is a generic description. And the degree of this line bundle, you can calculate also. This is D plus n times n minus 1 times g minus 1. This is one could call D hat, it's independent of A. And P star, there is, I should have given a name to the projection of this line bundle, so of this ramified cover. I should call it little p. So if I push it down, then I get E. And there is also a way to recover phi. So at least this is E, and one also recover phi from CA and L. So the line bundle and the curve makes it possible to recover the Higgs field. The fourth thing maybe, well, okay, I will make it more precise in the proof. So, of course, it's not really a proof, but just an indication of proof. Well, first of all, I need to calculate the genus. So what I do is, without proof, but this is rather easy to check. What I do is I take the direct image of the structure sheet, and I can calculate it in terms of line bundles. It splits, and this is just because of the construction of CA. You can quite easily see that it is the direct sum of omega C minus 1 plus omega C minus 10 over n. And then you apply Riemann-Roch. And the same calculation, you get that H1 of P star is H1. Is H1 of OCA on the one hand, on the other hand, it's just sum of the H1 of omega C minus J. J is 0. Oh well, there is something wrong. No, it's okay. And here you get the same calculation as before, it gives you dA. So this is easy. This proves that the genus is correct. And then for 2, I have to make everything canonical. So how to do this? Well, so canonical construction. The canonical construction is as follows. You do, maybe I should end here with n minus 1, I'm not so sure now. Should be probably n minus 1. I think n minus 1. Now there is a canonical construction, namely what I do is it's very nice. You take, I will also call it P, the cotangent bundle, the total space of the cotangent bundle projects to C, and now I have my canonical bundle here, and I can lift the canonical bundle upstairs, and this line bundle has a canonical section. So P star omega has a canonical section. Which I will call lambda. And now, if I write down P at where I replace the x's by the lambda, so then I get lambda to the n plus P star A1 lambda to the power n minus 1 plus P star An. This now becomes a section, another section in P upper star omega to the n. Now what I do is I just take the zeros of this section. So where this section is 0, this is a surface. So the zeros of this section will define a curve. So this is my curve CA. This is what it should be, because its zeros give the lambda 1 to lambda n. So this is exactly, makes precise what I did before. So here I have my curve sitting in, projects under P to C. And the point lying over x are exactly the roots lambda 1 up to lambda n at the point x by construction. So it's very nice. So this gives a canonical construction. And now you also see that you have the vector bundle E. You can lift it to here. And inside it makes sense to look at the eigenspaces. So these eigenspaces give, they assemble here to one line bundle.
The eigenspaces for what?
The eigenspaces for the operator phi. Yeah? So you, phi still acts, and the eigenspaces then canonically give a subline bundle of p star of so eigenspace of phi correspond to a subline bundle L A inside P upper star of E. And in fact, this is not entirely true. This is not entirely true. There is a small glitch here, namely, I assume this would be true if there are no ramification points. So this is not entirely true. So I'm glossing over a point. But I don't have time to explain this. So this would be true if there is no ramification, but you can easily correct it.
And so which, is it a particular eigenspace of phi, like with some given eigenvalue, or?
No, all.
Or
Yeah, because the points, they parameterize all the eigenvalues.
oh,
Yes.
okay. Yep, I see.
Okay, now for going back, you have to, so the operator phi corresponds to multiplying with lambda. So if you push it down to C again, it becomes the operator phi. So multiplication with lambda upstairs on this line bundle, downstairs gives phi. So you have upstairs LA goes to LA 10 to omega. It is multiplication by lambda. And downstairs it gives phi. And now, because phi satisfies its characteristic equation, you, if you start with the construction here, it must satisfy the characteristic equation, so it must be the original phi you started with. So if you start with, if you start here with something, a line bundle, you have this is independent of phi. This is always there, lambda. So you can start with a line bundle and this lambda, which is a canonical section, has nothing to do with E. Then you push it downstairs, you get an operator, and this operator must, by construction, be must satisfy the characteristic equation. So by Cayley-Hamilton, it must be the original thing that you have if you started with phi.
There's no problem about like semi-simplification
Huh?
or so? There's no sort of issue with semi-simplification?
No.
Okay.
Now, no, because Cayley-Hamilton is true for non-semi-simple things as well. So now there is one point which is a bit annoying, and this is I have to spend the last 10 minutes about this because it's quite subtle. Because remember what I did. I started with any line bundle, who guarantees me that if I push it down, that it's stable? Yes? And in general, it won't. I will give an example. So, if I start just with any line bundle, then I'm bound to fail. So, if I do this Hitchin construction with stable vector bundles, so on the cotangent space, cotangent bundle, I never will get the entire Jacobian as fiber. Only an open part, namely those for which the direct image gives a stable line bundle. How do I solve this problem? By not looking at stable vector bundles, but by looking at stable pairs, namely stable bundles with an operator phi. So a stable Higgs bundle. That's the difference. If I do that, then I'm saved. Because why do I get for any line model something stable here? Well, this, again, very nice. If I take the direct image of such a thing, then I get a phi. So